Hello everyone, myself Riya Jain. My roll number is IT2K2049 and this video is a part of my assignment given to us by Dr. Shaligram Prajapat sir, and in this video I am going to provide the solution of first internal test paper. So let's start. The first question is complete the table 1.0 after simplification of the corresponding recurrence relation. Here we have given a table and we have to complete this table by filling the time complexity, space complexity and power complexity of the corresponding algorithms. We can see the explanation of this question here. First, we discuss what is time complexity, space complexity and power complexity of an algorithm. Time complexity may depend on various factors such as the specific input to the algorithm, the efficiency of the implementation and the use of any auxiliary data structure or algorithm. In practice, the actual running time of an algorithm may also be affected by various external factors such as hardware limitation, operating system overhead, and the size of the input data. Space complexity. Space complexity may also depend on other factors such as the implementation details and the specific input to the algorithm. In some cases, the space complexity may also be affected by the use of auxiliary data structures or temporary variables. The power complexity of an algorithm is a measure of how the algorithm's running time grows as the input size increases. It is typically expressed in terms of the exponent in the running time's big O notation. Note that the power complexity of the algorithm are not the same as their time or space complexities. The time and space complexities may have different constants or lower order terms that affect the actual running time or memory uses of the algorithm. Now, the first algorithm is linear search. The recurrence relation for the linear search is given by T of n is equals to T of n minus 1 plus order of C, where n is the size of the input and C is the constant time taken to compare an element in the list with the target element. To solve this recurrence relation, we use the recursive tree method. By solving this recurrence relation, we get the time complexity of linear search algorithm is order of n. The space complexity of linear search algorithm is order of 1 because it does not require any additional space beyond the input list and a few constant variables used for indexing and comparisons. The power complexity of linear search is order of n, which means that the running time of an algorithm grows linearly with the size of the input data. Second algorithm is binary search. The recurrence relation for the binary search algorithm is given by T of n is equals to T of n by 2 plus order of C, where n is the size of the input and C is the constant time taken to compare an element in the list with the target element. By solving this recurrence relation using Master's theorem, we get the time complexity of binary search algorithm is order of 1. This is because the algorithm divides the input size in half at each step, so the number of steps required is log n, which is a constant factor. The space complexity of binary search algorithm is order of 1 because it does not require any additional space beyond the input list. The power complexity of binary search algorithm is order of log n, which means that the running time of an algorithm grows logarithmically with the size of the input data. The third algorithm is factorial function. The recurrence relation for this algorithm is given by T of n is equals to T of n minus 1 plus order of C, where n is the input to the factorial function and C is the constant time taken to perform a multiplication operation. We can solve this recurrence relation using recursive tree method and we get the time complexity of factorial function is order of n. This is because the function call itself recursively n times and performs a multiplication operation in each call. The space complexity of the factorial function is order of n because the function call itself recursively n times. The power complexity of recursive factorial function is order of n, which means that the running time of the algorithm grows linearly with the size of the input data. The fourth algorithm is Tower of Hanoi problem. The recurrence relation for this algorithm is given by T of n is equals to 2T of n minus 1 plus order of C, where n is the number of disks to be moved and C is the constant time taken to perform a disk move. We can solve this recurrence relation using recursive tree method, and by solving this recurrence relation we get the time complexity of Tower of Hanoi problem is order of 2 to the power n. This is because in worst case the algorithm needs to make 2 to the power n minus 1 disk moves to complete the problem. The space complexity of Tower of Hanoi problem is order of n because the function call itself recursively n times and each call creates a new state frame on the call stack. The power complexity of Tower of Hanoi algorithm is order of 2 to the power n, which means that the running time of algorithm grows exponentially with the size of the input data. The fifth algorithm is binary tree traversal. The recurrence relation for this algorithm is given by T of n is equals to 2T of n by 2 plus order of 1, where n is the number of nodes in the binary tree and order of 1 is the constant time taken to process a node. To solve this recurrence relation, we can use the Master's theorem. By solving this using Master's theorem, we get the time complexity of binary tree traversal is order of n log n. The space complexity of this algorithm depends on the implementation of the traversal algorithm. If the algorithm uses an explicit stack to maintain the traversal order, then the space complexity is order of h, where h is the height of the binary tree. If the algorithm uses the call stack for recursion, then the space complexity is order of log n, where n is the number of nodes in the binary tree. This is because the maximum depth of call stack is log n, which is the height of a balanced binary tree. The power complexity of binary tree traversal is order of n because the algorithm needs to process each nodes in the binary tree once. The sixth algorithm is merge sort. The recurrence relation for merge sort is given by T of n is equals to 2T of n by 2 plus order of n, where n is the number of elements to be sorted and order of n is the time taken to merge two sorted arrays of size n by 2. We can solve this recurrence relation using Master's theorem. By solving this recurrence relation, we get the time complexity of merge sort is order of n log n. The space complexity of merge sort is order of n because the algorithm needs to create a temporary array to store the element being merged during the merge phase of the algorithm. The power complexity of merge sort is order of n log n because the algorithm needs to perform n log n comparison and swaps in the worst case. Now the seventh algorithm is quick sort. The recurrence relation of quick sort in best case is given by T of n is equals to 2T n by 2 plus order of n. By solving this recurrence relation, we get the time complexity of quick sort in the best case is order of n log n. The space complexity of quicksort depend on the implementation. In the simplest implementation, the space complexity is order of log n due to the recursive calls, but in the worst case, it can be order of n due to the stack space used by the recursion. However, in the best case, the space complexity is order of log n. The power complexity of quicksort in its best case is order of n log n because the algorithm needs to perform n log n comparison and swaps in the best case. The recurrence relation for quicksort in its worst case is given by T of n is equals to T of n minus 1 T of n minus 1 plus order of n square. Therefore, the time complexity of quicksort in its worst case is order of n square. The space complexity of quicksort in its worst case is order of n due to the recursive call since the depth of the recursion tree is n. The power complexity of quicksort in its worst case is order of n to the power 3 since the algorithm needs to perform n square comparison and swaps the sweeps and the recursion tree has depth n. The eighth algorithm is Stressen's matrix multiplication. The recurrence relation for this algorithm is given by T of n is equals to 7t of n by 2 plus order of n square. By solving this recurrence relation, we get the time complexity of this algorithm is order of n to the power 2.81. The space complexity of this algorithm is order of n to the power 2.81, which is the same as the time complexity since the algorithm uses a recursive approach that requires the creation of new matrices. The power complexity of Stressen's matrix multiplication is order of n to the power 2.81 log n since the algorithm performs order of n to the power 2.81 scalar multiplication at each level of recursion tree and the depth of the recursion tree is log n. The ninth algorithm is Karatsuba integer multiplication. The recurrence relation for this algorithm is given by T of n is equals to 3t of n by 2 plus order of n square. By solving this recurrence relation using Master's theorem, we get the time complexity of this algorithm as order of n to the power 1.585. The space complexity of this algorithm is given by order of n to the power 1.585. The power complexity of this algorithm is given by order of n to the power 1.585 log n. Since the algorithm performs order of n to the power 1.585 multiplication at each level of the recursion tree and the depth of the recursion tree is log n. Now we move to the question second, and the second question is write recursive algorithm for polynomial representation. This algorithm defines a class polynomial with a constructor that takes a list of coefficients. The evaluate method evaluates the polynomial for a given value of x. The base case of the recursion is when the polynomial has degree 0, that is, it is a constant polynomial. In this case, the method simply returns the single coefficient. In the recursive case, the method creates a new polynomial p of degree n minus 1 by removing the highest degree coefficient from the list of the coefficient. It then recursively evaluates p for the given value of x and multiplies the result by x. Finally, it adds the highest degree coefficient to obtain the value of the polynomial for the given value of x. The algorithm works by breaking down the problem of evaluating a polynomial of degree n into the problem of evaluating a polynomial of degree n minus 1. It uses the fact that a polynomial of degree n can be expressed as a p of x is equals to x into q of x plus c, where q of x is a polynomial of degree n minus 1 and c is the highest degree coefficient. This allows the evaluation to be performed recursively by computing q of x and multiplying by x and then adding the highest degree coefficient. And here is the recursive algorithm for polynomial representation. Now, the question third is write iterative version of Tower of Hanoi problem. This implementation uses a stack to keep track of the recursive calls that would be made in the recursive version. The stack starts with the initial call to move n disk from the from rod to the to rod, using the auxiliary rod as an intermediate rod. In each iteration of the loop, the top call is popped from the stack and executed. If there is only one disk to move, it is moved and the loop continues. Otherwise, two recursive calls are pushed onto the stack. One to move n-1 disk from the from rod to auxiliary rod using the to rod as an intermediate rod, and another to move the n-1 disk from the auxiliary rod to the to rod using the from rod as an intermediate rod. Finally, the call to move the remaining disk from the from rod to the to rod is also pushed onto the stack. This process continues until the stack is empty, at which point all the necessary moves have been made to solve the Tower of Hanoi problem. And here is the iterative version of Tower of Hanoi problem. This algorithm is the iterative version of Tower of Hanoi problem. Thank you for watching.